The Netherlands begins where dry land should surrender to the North Sea.
Behind this dike, entire communities live beneath the surrounding waterline.
Today, we reveal how engineers built a country that should not exist.
Northwesterly storms can push billions of tons of water toward this coast. This enormous defense system stands between violent water and vulnerable land.
Every impact transfers immense pressure through concrete, steel, rock, and foundation soil.
The danger is not distant. Gravity constantly favors the water. Behind the barrier, ordinary life continues only because water remains controlled.
Yet Rotterdam's shipping route could never be sealed by a permanent dam.
How could engineers stop the sea without stopping the nation itself?
In 1953, storm winds and high tides created a deadly combination.
Once water crossed the crest, erosion rapidly attacked the dike from behind. The flood killed 1,836 people and displaced tens of thousands.
The disaster proved that isolated repairs could no longer guarantee national safety.
Investigators traced the catastrophe through storm levels, weak barriers, and exposed estuaries. Their strategy shortened the coastline by defending estuary entrances farther seaward.
Rotterdam required permanent flood protection without sacrificing its vital maritime corridor.
Closing every inlet would destroy tides, fisheries, and valuable saltwater habitats.
The final system had to protect people while preserving water, trade, and nature.
The solution would become a network, not merely one enormous wall.
Survey crews first mapped every channel, sandbank, and underwater slope.
Sonar revealed irregular channels where foundations would face concentrated tidal currents.
Current meters recorded direction, velocity, and pressure throughout complete tidal cycles.
Boreholes exposed the hidden soil layers beneath the proposed barrier alignment.
Laboratory testing determined which layers could carry colossal concrete piers safely.
Divers documented damaged foundations, marine growth, and vulnerable erosion zones.
Historic weather data defined the forces the structure must survive repeatedly.
Physical models showed how each design would redirect waves and tidal currents.
Precise elevation mapping identified every community threatened by barrier failure.
Environmental surveys measured what a permanently closed estuary would lose.
The surveys revealed a hidden enemy, moving sediment beneath the structure. Every construction decision now depended on water, soil, weather, and ecology together. The simplest option was a solid dam extending completely across the estuary.
But permanent closure would eliminate the natural tidal exchange almost entirely.
That solution protected land while threatening fisheries, habitats, and coastal livelihoods.
At Rotterdam, a fixed wall would cripple Europe's busiest maritime gateway.
Movable gates solved access problems but introduced enormous bending and vibration loads.
Each pier required stable support on a seabed that naturally shifted.
Saltwater threatened every exposed plate, cable, bearing, seal, and mechanical connection. Small placement errors could prevent the steel gates from fitting correctly. Restricted flow could accelerate beneath the gates and excavate the seabed. Rotterdam's movable barrier required joints capable of rotating under extreme loading.
The barriers also needed reliable closure during electricity and communication failures.
The project demanded strength, movement, precision, and environmental balance simultaneously.
Design teams compared protection, cost, construction risk, navigation, and environmental impact.
An open, movable barrier preserved tides while providing protection during extreme storms. The completed Eastern Scheldt defense would extend approximately 9 kilometers.
65 concrete piers would support 62 independently movable steel gates.
Hollow piers reduced weight while carrying wave forces into broad foundations. Each gate required exceptional stiffness without becoming impossible to lift or maintain.
Engineered bedding distributed weight and protected the seabed from concentrated currents.
A purpose-built island transformed open water into an industrial construction platform.
At Rotterdam, 2 swinging gates could leave shipping completely unobstructed. Each gate rotates through a 680-ton ball and socket joint. Independent systems reduced the chance that one failure could disable everything.
The Netherlands chose movable engineering instead of permanently surrendering its waterways. Dredgers first created stable working ground inside the exposed tidal environment.
Temporary barriers isolated the casting area from tides and storm waves.
A temporary harbor connected offshore construction with mainland supply chains.
On-site production ensured continuous concrete quality for the massive pier program. Reinforcement yards prepared thousands of precisely positioned bars and welded assemblies.
The building dock had to remain dry throughout years of concrete casting.
Internal roads kept concrete, steel, workers and equipment moving without conflict. Temporary utilities supported fabrication, pumping, lighting, welding, and emergency response. Real-time forecasting determined when offshore lifting could proceed safely.
The artificial island was now ready to manufacture structures on an unprecedented scale.
Pier construction began with reinforced skeletons designed to control cracking and load.
Reusable climbing forms allowed the concrete walls to rise in controlled stages.
Continuous placement prevented weak joints inside the heavily loaded pier walls.
Controlled curing limited thermal cracking within these unusually thick concrete sections.
Gate fabrication began by cutting high-strength steel into precisely calculated profiles.
Deep structural welds transformed separate plates into rigid hollow gate assemblies. Machined interfaces ensured each gate would travel smoothly between concrete slots.
Flexible components controlled leakage, vibration, and metal contact during repeated closures.
Protective coatings isolated the steel from decades of saltwater corrosion.
Internal inspections confirmed structural continuity before the pier entered the water.
Mechanical systems connected the movable gates with inspection and maintenance infrastructure.
Flooding the dock converted each finished pier into a transportable floating structure.
Years of manufacturing had produced every major component required offshore.
And offshore construction began by shaping a consistent foundation trench beneath moving water. Graded stone created a level, drainable platform above the weaker sediment. Protective mattresses separated foundation materials and resisted erosion beneath strong currents. Each mattress had to land smoothly, without folds, gaps, or trapped sediment.
Stone ballast locked the foundation protection against lifting and tidal displacement.
Tugs moved the enormous pier only during a carefully selected tidal window. And
coordinated tow lines controlled rotation while currents pushed against the hollow structure. Cole Harris used continuous positioning data to align the pier above its foundation. Controlled ballast transformed the floating pier into a steadily descending foundation block. Uneven ballast corrections kept the structure level during its final descent. Engineers verified position, elevation, and vertical alignment before releasing installation cables. The process repeated methodically until 3 open barrier sections crossed the estuary. Once adjacent piers were stable, installation shifted to the movable steel gates. The lift required calm weather, balanced rigging, and continuous wind monitoring. Millimeter-scale guidance prevented the gate from striking either reinforced concrete edge. Mechanical connections converted the installed gate into a controllable flood defense component. Upper structures linked the barrier while providing road and maintenance access. Continuous service corridors allowed technicians to inspect the barrier from within.
a separate construction program formed Rotterdam's 2 giant movable storm gates.
The arms transferred water pressure from each door into its spherical foundation joint.
Mobile drives pushed each gate from its dock toward the channel center.
Concrete, steel, and machinery now formed an interconnected national defense system.
A routine sonar inspection suddenly revealed a dangerous void beneath the foundation.
Accelerated current had carried sediment away faster than crews anticipated.
Even slight rotation could misalign the gate slots and overload neighboring structures. Temporary cables slowed movement, but could not replace a stable foundation.
Cole immediately stopped heavy operations before additional loads reached the pier.
Ryan cleared the danger zone and restricted all non-essential marine traffic.
Jack halted production deliveries until engineers could guarantee structural stability.
Liam combined seabed data with movement records to identify the failure mechanism. The repair window was narrowing as another storm approached the estuary.
The team chose to rebuild support without lifting the pier again.
Detailed inspection defined the cavity's depth, shape, and remaining bearing zones.
Engineers drilled injection paths through areas designed to tolerate local penetration.
Multiple injection pipes distributed repair material across the complete unsupported area.
Pressure-controlled grout displaced water and filled the void from its deepest point.
New anchors resisted rotation while the repaired foundation gained strength. An enlarged rock apron reduced current velocity directly beside the foundation. Sensors confirmed that curing progressed evenly without renewed settlement or pressure loss.
Emma verified continuity, material strength, and contact across the repaired foundation. A proof test confirmed that the pier remained stable under simulated storm loading.
Only after verification did Liam release the project to continue safely.
Mechanical gates became operational only after receiving controlled movement and position feedback.
Dual measurements revealed the pressure difference acting across every closed gate.
Remote instruments continuously measured the storm before it reached the barrier.
One control center transformed separate structures into a coordinated protective system.
Forecasting software determines when automatic closure becomes necessary near Rotterdam.
Redundant power allowed essential functions to continue during widespread electrical failure. Manual systems remained available if automatic commands or communications ever failed.
Coastal barriers worked together with pumps, canals, dikes, and river controls.
Reliable communication delivered warnings before rising water reached critical levels.
The completed structures now operated as one integrated national water defense network.
Engineers first tested each gate individually through its complete operating range.
The full trial synchronized 62 gates without creating dangerous hydraulic imbalance.
Operators confirmed that complete closure could be achieved within approximately 7 to 5 minutes.
Wave testing measured structural response beyond conditions expected during normal operation.
Simulated power failure proved that critical systems could continue independently.
Rotterdam's final trial began by swinging both doors across the navigation channel.
Controlled flooding increased their weight until the doors settled onto the bottom. Leakage measurements verified continuous contact across the submerged ceiling line.
Every measurement was reviewed before the barriers could receive operational approval. The final results confirmed that both systems were ready for real storms.
In 2023, extreme water forecasts triggered the first full automatic storm closure, the computer-initiated closure, while trained teams monitored every movement and alarm. Once submerged, the gates formed a temporary wall against the surge. Outside, the sea remained violent. Behind the system, daily life continued.
When danger passed, the barrier reopened, and international shipping resumed.
They did not defeat the sea. They engineered a nation able to live beside it.